بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. In this tutorial series, we will be looking at the modeling and simulation of planar manipulators using MATLAB as part of the geometric modeling and control of robotic systems course at Jacobian. This tutorial series consists of a number of parts, each one dedicated to a certain aspect. For example, we'll be looking at the forward kinematics and the differential kinematics, deriving them symbolically. And then we're going to be looking at the dynamic equations, how we can derive them also symbolically. And then we're going to be looking at the simulation and the numerical computation of these matrices and these variables using the robotic systems toolbox of MATLAB. Okay, so we're going to be starting immediately. In this first tutorial, we'll be looking at a planar 3-link manipulator as the one that you see here on the screen. We'll be deriving its forward kinematics and differential kinematics using the Lie group approach. So let's start. So what you see here in front of you, this is a live script of MATLAB. So we'll be running it as we go. So I already ran it before. So let me first just remove all of the output so that you can have a clean file. So you see here, we have a text and code within the file, and this is an interactive file, so we can change stuff and try different stuff along the way. So in this tutorial, we're going to be starting by just some preparation stuff. We're going to be closing and clearing everything in the workspace. And then we're going to be loading the modern robotics MATLAB package. So this is a MATLAB package that's developed as part of the modern robotics book by Kevin Lynch and Frank Park. And if we just take a look at this package, you're going to find that they already implemented a lot of functions that are useful for the Lie group approach to modeling and simulating manipulators. So we'll be using this package, and we're going to be going through the functions that we use from this package along the way. We also add the path to another folder that consists of helper functions that are actually auxiliary and were not implemented in the modern robotics package, but we do use them here in the course. So this is part of, so these are built-in, so these are actually custom-made MATLAB functions, and we'll also go through them along the way. So the first thing we're going to be doing, so in this tutorial, we'll be deriving the forward kinematics and the differential kinematics symbolically. So for that, we're going to be defining the symbolic variables. We're going to have L1, L2, and L3. We define them as real variables, symbolic variables. So L1 and L2 and L3, they correspond, as you see here in this picture, to the length of the 3 links of the manipulator. We also have Q1 and Q2 and Q3, which correspond to the angles of each joint. So you see here, we have one joint between the first link and the base of the robot. We have a second joint between the second link and the first link. We have the third joint between the third link and the second link. The first to derive. So first, okay. So now to run this, I'm going to be using Control Enter. So Control Enter will only run this section here. So you see this blue part that starts with that ends here. Actually consists of these two code blocks. So now when we pressed Control Enter, we actually ran these two. There's nothing that happened, okay? So we have nothing to see. The first thing we're going to be doing to derive the forward kinematics, we're going to be using a product of exponentials formula. And if you remember from the lecture, it requires very few inputs. And all of these inputs that the product of exponentials formula requires is simply the home configuration of the end effector frame with respect to the base frame. So this is the home configuration that we choose. So we choose that if the row of the manipulator is in this configuration, which is the horizontal pose of the 3 links. This is what we call the home configuration. And in this home configuration, we need to define the end effector pose with respect to the base of the robot. And we also need to define the screw axis of the 3 joints as seen from the base of the robot. So the 0 frame. This is the stationary frame. So with respect to the home configuration, so we define it like this. If you look at the figure here, you see that the end effector frame and the 0 frame, they both have the same orientation. So R of E with respect to 0. So this is the notation we're going to be using here. So R of E with respect to 0 is an identity. So they both have the same orientation. And the displacement of the end effector frame, the origin of the end effector frame, as seen from the 0 frame, okay, is simply given by L1 plus L2 plus L3 in the first direction, in the X direction. Okay, and it's a convention that the frames, they have R as the X direction, so red and green and blue, so R, G, and B. So the red direction here is simply the X direction of the frame. So if you look at here, and we move in the X direction of the 0 frame by L1 plus L2 plus 3, and then we reach the origin, and there is no displacement in the Y or the Z direction. So thus we have L1 plus L2 plus L3 and 0 and 0. Then we're going to be taking the rotation matrix and this displacement vector, and we're going to be putting them into a homogeneous transformation matrix. We're going to be calling this H of E with respect to 0 home. Okay, so you see here, this variable corresponds to the homogeneous transformation of the end effector frame with respect to the 0 frame in the home configuration. Okay, when all of the joints are 0. So this is what we call it. This RP to trans, this is a function that comes from the MATLAB package of the modern robotics. And if you look at it, what it has inside is that simply takes the R alone and the P alone and just constructs the homogeneous transformation matrix. It's as simple as that, but it's very useful. So if we run this block, what you see here is that the home configuration, the pose of the end effector in the home configuration looks like this. Okay? It's simply identity of rotation, and we have L1 plus L2 plus L3 at the edge. So that's it. That's the first part. And now if we look at the screw axes of the 3 joints, S1 with respect to 0, S2 with respect to 1, and S3 with respect to 2, all of them expressed in the 0 frame. They're all expressed in the base frame. We're going to be defining them as follows. If you look at this picture, then all of the 3 axes, they are rotating around the Z. Okay, so they're all rotation around the Z, rotation around the blue axis of the base. And thus, if you look at the N axis here, so this is N of 1 with respect to 0 expressed in 0. This is N of 2 with respect to 1 expressed in 0. This is N of 3 with respect to 2 expressed in 0. Okay, so these are the axes of rotation, which are all the Z axis. So there are the third axis, 0, 0, and 1, 0, 0, and 1, and 0, 0, and 1. They're all the same. And R here is any point on the axis. You just need to choose any point, as you've seen in the lecture, and this will correspond. Pairing these two will actually allow us to calculate the screw axis, okay, in a straightforward manner. So the point, if you look at the first axis here, so S1 with respect to 0, we see that actually it passes through the 0. So it passes through the origin, which means actually the point that we easily can choose is simply 0, 0, and 0. This is what we do here. And this one, the point we're going to be choosing is this one. So actually the coordinates of this point is simply on this axis is simply L1 in the X direction and 0, 0. And the point that we're going to be choosing here is this one, which is L1 plus L2 in the X direction. Okay, and this is what the point that we choose on the third screw axis. And then we take these two, the pairs, and then we create from them the screw axis as follows. So if you look at this screw axis, this is a function. This is not part of the modern robotics package, but part of our course package. You see, it simply takes the n hat, okay, the unit vector that we had, and puts it first, and then it takes the cross product of R of this point that we provided and the n hat. Okay, so that's simply what this screw axis does. And we can also print. So now we can actually print. So let's run this and print the screw axis expressed in 0. You see, in the first case, we have 0, 0, and 1, and 3 zeros, because it's the cross product of the point that we chose, which is 0, and 0, 0, 1 is 0. If you look at the second case, you see that the second screw axis, we see that the L1 here was in positive X, but this was the point. The 3 components of the screw axis are actually coming from the cross product of L1 and 0 with 0, 0, and 1. Okay, so we had cross product of something in the X with something in the Z, and thus we get something in the minus Y. Okay? And the same also for the third square. These are, so what we did so far is that we took the home configuration and we defined only 4 quantities, which is simply H, E with respect to 0 in the home configuration, and in the 3 screw axes of the joints. This is all the information we need to run the product of exponential formulas, and the product of exponential formulas, the product of exponentials formula will allow us to compute the forward kinematics map, which is simply given Q1 and Q2 and Q3. Okay, what is the end effector pose? Okay. So this function, and now if we run it here, we simply see that it's nothing else than the exponential of we have an exponential of SE3. So this is actually a map that's the function that's defined. We're going to take a look at it in a bit. So this is how we write the exponential. It takes as an input S1 with respect to 0 expressed in 0. So this quantity, and it takes the Q1 angle. So remember the Q1 here, we defined it actually to be symbolic. So we defined here Q1 and Q2 and 3 to be symbolic joint angles, which in the end, the expression that we get here for HE with respect to 0. And simply what we do here is that actually we just extract the rotation part and the psi part. So trans to RP is nothing else than the inverse map of RP to trans. Okay, so here you give a rotation matrix and a position vector, and it transforms it into a homogeneous transformation, while here it's the inverse. So if we look at the rotation matrix and the position of the end effector, of the origin of the end effector frame, you see that it's given by these expressions, and they're all computed simply in this one line. Okay, we had here a simplify, okay, just so that when we compute these exponential maps, we can actually use trigonometric identities just to get this compact form of the forward kinematics map. This is the same expression. Actually, it also makes sense simply by, if you just take a look here by this picture, you see actually that the x location of the end effector frame is simply L1 cosine, the angle Q1, L2 plus L2 cosine plus L3 cosine, the third angle. And simply, this is just the term that we have here. So we have L1 in the x direction, we have L1 cosine Q1, L2 cosine Q1 plus Q2, and L3 cosine Q1 plus Q2 and Q3. We have the signs on the y direction. And actually, these formulas you're going to find they actually match with the ones that are in that we covered in the lecture. Let's take a look at what's inside of this exponential map. So this exponential map is implemented in the MATLAB package of the modern robotics course, of the modern robotics book. And you see here, it has it takes a screw axis and it takes the angle, and it returns in the end the homogeneous transformation matrix using the exponential map. And inside of it here, it simply actually implements both cases. So if you remember, the exponential map depends on whether you actually have like a pure rotation or a pure translation through axis. There's also even a third case if you have a pitch motion, but this is not covered here. So you simply have here, this is the case if this is the pure translation, and this is the case if you have a pure rotation. Inside of this pure rotation case, we actually have the rotation matrix computed by the exponential map of SO3. And this is another function that's in the package. And if you look at it, you find actually the exponential map of SO3 is simply given by, this is the Rodriguez formula. Okay, so you can take a look at it at your own pace. So this is simply the Rodriguez formula, and the omega mat is simply the matrix representation of the axis. And this is actually nothing else than the skew symmetric representation of the vector. Okay, so SO3 matrix is simply, so this is, it takes a 3 vector and returns its skew symmetric form in SO3 of this vector. Okay, so we're going to be using this vector SO3, we're going to find it a lot. Just small point that actually this exponential map of SO3 is not the one that's from the MATLAB package, neither the one from neither the exponential SE3 one. These are actually both custom ones. They are very similar to the one that's in the modern robotics package, but we actually modified them in this course so that we're able to compute the exponential map symbolically. So the modern robotics package, it only allows you to compute numerically, but we just modified it here so that we're able to do symbolic computation of it. So this is why we got here in the end the forward kinematics map. It's as simple as this. So now we're done. That's it. So that's the forward kinematics part. Let's look at now an alternative way of computing the same expression. Okay. And this alternative way actually is simply another version of the product exponentials formula, but not with all of the screw axes, not defined in the base frame, but actually defined in the end effector frame. So we could have alternatively instead of expressed the three axes here, that the ones that you see in orange. In the zero frame, we could have alternatively expressed them in the E frame. And this is exactly what you see here in this section. So what we do here is that we represent the three screw axes in the end effector frame. And thus, if you look at the axis of rotation is the same. We're still rotating around the Z axis. The reason for that is because the end effector Z axis is the same as the base Z axis, so that's the same. So there's nothing new there. While the point here of the axis, the point on the axis expressed with respect to E now is different actually from zero. For example, you see here that the first screw axis passed through the origin of the zero frame, and thus we had here 0 and 0 and 0 as the point that we choose on the axis. However, if we represent it in the E frame, actually the point here will be given by minus L3, minus L2, and minus L1 in the X direction. And that's exactly what you see here in this part, that actually have minus L1, minus L2, and minus L3 in the X direction. If you look at how the second axis of the second joint is expressed in the E frame, you'll find it's given by this expression, and this is how it's represented in the. This is how the third axis is represented in the E frame. Okay, now if we run this and we take a look at the expressions, you see actually that now this is the screw axis of the same joint. So be aware that actually that what you see here, 0, 0, and 1, and 0, L1 plus L2 plus L3 and 0, we're talking about the same axis. So this is the same screw axis from 1 with respect to 0. Though this is the same one that we looked at here. The only difference is that in this expression, these are the coordinates of this screw axis expressed in the zero frame, while these are the coordinates of this screw axis expressed in the E frame. And of course, it's the same abstract vector, it's the same this screw axis. However, if you represent it in two different frames, you get different numbers. That's the only difference you see here. The product of exponentials formula that uses the screw axis expressed in the E frame is different. Okay, it has this reversed order. So we have E, so we have the exponential of the first axis, exponential of the second axis, exponential of the third axis, and we have a pre-multiplication of the home configuration, the home poles. Okay, so this is the difference here. You see here, this expression is slightly different from that one. And the only difference is that here, the screw axes, they are expressed in different frames. Okay, and of course, you should expect that if we run this expression, now we get exactly the same forward kinematics map. So if you compare this rotation matrix and this displacement vector to the one that we computed here, they are exactly the same, nothing different. Okay, without any signs or anything. Okay. So that's it. So far we covered the forward kinematics. We did it in two different ways. Now let's look very briefly at the differential kinematics. Differential kinematics is simply encoded in the geometric spatial Jacobian. So JE with respect to 0 expressed in 0. And since we have a 3-link manipulator, it's a 6x3 matrix, which means it has 3 columns, and each column is a 6x1 vector. And these 3 columns are simply screw axes, but are transformed by using some adjoint matrix. So we see here, this is the first column of the adjoint, first column of the Jacobian, second column of the Jacobian, and third column of the Jacobian. And simply in this expression, we just simplify a little bit. If you look at it, you'll see actually it looks like this. And you see that this is actually a recurrent. This is also what you see here is actually something that it happens for any N-link manipulator, especially if it's a serial linkage. That actually the first column of the J of the spatial Jacobian is a constant. It doesn't depend on Q1 nor Q2 nor Q3. The second column depends only on Q1. The third column only depends on Q1 and Q2, and so on and so forth. So if we have the ith column, it will depend on Q1 up to Qi minus 1. Okay, so as you've seen in the lecture, so we have this the equation of that we presented in the lecture. You can take a look at it, and you'll see that actually this is simply how we compute the columns of the spatial Jacobian. The body Jacobian will play a very important role. You're going to see later. We're going to be using actually that for control. And you can actually do a lot of analysis of this manipulator using this geometric Jacobian, whether the spatial one or the body one. The body one is simply computed, just transforming all of the columns of the JE with respect to E0 expressed in the zero frame from 0 to E, and transforming screw axes or twists in general from the 0 to the from any frame, which is in this case from 0 to E, is simply using the adjoint transformation. Okay, so the adjoint transformation here, if we actually open this adjoint transformation, you'll find that this is nothing else than the joint map of SE3. Okay, so we have here, it's a 6x6 matrix. You find that we have rotation matrix, and then we have zeros on this rotation matrix is on the top left corner. Top right corner, we have zeros. Bottom left corner, we have the P tilde, or like the displacement part of the homogeneous transformation matrix, as we put it in a tilde form, multiplied by the rotation matrix. And in the bottom right corner, we have the R, the rotation matrix again. Okay, so this is simply what the adjoint, how it looks like. And we want to transform here from the zero frame to the end effector frame. And thus we need to multiply it by the adjoint of H from 0 to E. We don't have the adjoint from 0 to E. We only calculated in the forward kinematics here from E to 0, but simply we can invert this matrix. We don't need to invert the 4x4 matrix. Actually, we can, because this is a homogeneous transformation, we can actually do, we can implement this in, it has the inverse has a closed form expression that's very efficient to compute. We open this trans inverse, you'll find that it's simply, okay, this expression for the inverse of homogeneous transformation matrix that you should be familiar with. Okay. And in the end, we also simplify it a little bit. And this is how the body Jacobian, the geometric body Jacobian looks like in the end effector. Okay, so that's it. So that's the end of the first tutorial. What we covered so far was the forward kinematics and the differential kinematics of this 3-link planar manipulator.